Okay, good afternoon, everyone. My name is Sashank, and I'm a graduate student at the University of Western Ontario in Canada. And today I'm going to try to convince you that looking beyond the optical spectrum, particularly in radio wavelength, is important for lunar surface missions. A little bit of background before we get started. The data I'll be using, I use for this study primarily comes from the Mini-RF instrument, which is the miniature radio frequency instrument located on the Lunar Reconnaissance Orbiter. Mini-RF initially flew aboard LRO in 2009 and collected a good amount of data from the lunar surface. It operated in S and X band, two different wavelengths. It initially operated in a monostatic configuration, and it's highlighted here by that white circle. But what monostatic means is it was able to collect and receive data from the LRO spacecraft itself, but due to a subsequent amplifier anomaly, it has since been transferred to a bistatic configuration where it receives data reflected by the lunar surface but emitted from a ground-based antenna. Now, if you were to compare optical and radar wavelengths, optical wavelengths are primarily sensitive to the surface, the top of the surface, whereas radar can penetrate the subsurface and the near subsurface. So radar data can see where optical wavelengths simply cannot. So during this presentation, I will use terms like backscatter and light. Please note that I'm referring to radio light or radar light. So when we talk about backscatter, it's the amount of light reflected by the surface that is returned to the radio sensor or radar sensor. It depends on three main surface properties, but we're going to focus on roughness. Roughness is how smooth or rough a surface is. So if you ignore topography, or if you have a surface with not very interesting topography, the amount of backscatter, the signal that's reflected by the surface that's received back by the sensor, depends on how rough the surface is. In radar speak, more rough equals more bounce. So that means as the surface roughness increases, more signal may be reflected back to the sensor. So another thing that we also talk about when we talk about radar is radar albedo, which is the intensity of the roughness. The intensity of the backscatter, which is determined by these four bottom properties, but we're going to focus on polarization. If you ever used a pair of polarized sunglasses that reduce glare, you know what polarization is, but polarization describes how light propagates, the direction in which it propagates. Light waves can propagate linearly, meaning horizontally or vertically, circularly or elliptically. Mini-RF uses a combination known as a hybrid polarization configuration, meaning it transmits circular polarized waves and it receives linearly polarized waves. This configuration means that the information received by Mini-RF from the lunar surface can be used to understand the surface scattering mechanisms, meaning how the surface interacts with the radio waves. Before the surface scattering mechanisms can be derived, however, you need to understand what Stokes parameters are. These are four values that describe the polarization properties of the light signal. Mathematical expressions that use a combination of these four Stokes parameters can be used to generate other products, such as degree of polarization, degree of circularity, which may be combined to generate RGB images that describe by color what the polarization property of a given surface is. We'll talk more about what these colors mean as we get to the results, but first, let's talk about Mini-RF coverage. This map shows all the regions on the lunar surface that Mini-RF has taken data from. The different colors indicate different wavelengths and resolutions at which this data was collected. This study primarily focuses on S-band monostatic data, of which there is about 67% coverage in the equatorial regions, which includes 4 of the 6 Apollo missions that made it to the surface. Of the 4, I chose to start the analysis with Apollo 17. And that's what we're going to look at for the results. Before we dive into the results, however, here's a little bit of background and context. The image on the right shows the Apollo 17 landing site, particularly a region known as South Massif, which is that mountain you're seeing on the background. And on the left is the same image of the South Massif, but taken by the narrow angle camera on the Lunar Reconnaissance Orbiter. This is optical wavelength, 1.5 meter resolution. The reason I put up the optical image is because even before Apollo 17 took off, they had a similar resolution image of the landing site taken by Apollo 15 while that mission was orbiting in space around the moon. So this bright feature emanating from the base of the South Massif, southwest of Apollo 17 landing site, was interpreted to be a landslide even before Apollo 17 took off, based on the optical data that they had. And that landslide is outlined in the right side, in the right image, which is also an LRAC image, LROC-NAC image, excuse me. Now let's see what radar would see. Now the same landslide that was seen in the optical wavelength looks a little bit different in radio wavelengths. The boundary has actually changed, and the different colors here also indicate different scattering mechanisms, which can only be seen with radar. And if I were to overlay the boundaries of both optical and radio wavelengths, this is what they would look like. The white continuous line shows optical boundary, and the dashed line shows the radar MCI boundary. The different colors in the MCI image, as I mentioned earlier, correspond to different scattering mechanisms, or how the surface scattered the radio waves. The red corresponds to double bound scattering, and there's barely any of red, which is pretty common for the moon, meaning it would be, if there's a lot of red, it would be not a good place to land, as it's likely to be very blocky. There's a good amount of green, which indicates that there's volume scattering, meaning a differentiated or porous surface where the radar is penetrating in the near subsurface before returning to the sensor. And there's also a little bit of blue, but not very light blue. Very light blue would indicate, like, the signal is just bouncing and not coming back, or just bouncing just once. But here's a combination of blue and blue-green, which means it's a mixture of volume and single bounce scattering. The single bounce refers to how many times the radar signal bounces on the surface before it returns. Volume scattering, I like to think of it as, like, the signal enters the surface and bounces around a bit like a pinball and then returns to the sensor. Now, one of the primary conclusions that can be drawn from this data is that radar can see what optical wavelengths cannot see. And the Apollo 17 site in particular, the landslide, is stratigraphically differentiated as seen by the green color, which indicates volume scattering. This supports results from previous radar studies, particularly the MCI map that I showed you earlier, because this is not something novel that I've identified, but it just adds on to the overwhelming amount of evidence that radar can be used to understand the scattering mechanisms at scales such as landing site scales. And combining radar observations with optical data can significantly enhance landing site mapping efforts. It's almost as if using diverse perspectives contributes to a fuller picture. Who knew? So the logical next steps for this analysis would be to apply these methods to other available landing site data. So these are landing site maps from in MCI obtained by Caleb Fassett et al. In 2024. These are a little bit lower resolution. However, the high resolution data can be processed, and similar analysis to what I did can be applied to them as well. And the findings of the entire analysis for all the Apollo landing sites can be carried forward to future landing sites, including Artemis. And shown here is a map of the South Pole region, particularly the Artemis landing sites. And you can notice that in S-band monostatic data, NESF has observed almost the entirety of the Artemis candidate regions. And that brings me to the conclusion of my talk. Thank you so much for your attention. I would like to thank my supervisor, Catherine Nish, and the NESF team for helping me interpret the analysis, particularly Caleb Fassett. Left QR code is my LinkedIn profile. Please connect, so as I'll be looking for a job in about a year or so. And the right one is for my abstract. Thank you once again.